Hello everyone. So, let us move on to the fourth lecture of electromagnetic induction. I am Sameer Lavankar. So, let us begin. So, this was the course outline. The first was introduction part, in which we talked about what is electromagnetic induction, followed by the three experiments of Faraday and Henry, followed by magnetic flux. Phi b value was being talked about there. Faraday's laws of induction, in which the value, the definition or the formula of induced EMF, which is equal to minus n d phi b by dt, was being derived. Followed by Lenz's law and conservation of energy. The conservation of energy topic was being talked about. Why there is a negative sign here is being talked about in Lenz's law in lesson number 5. In the last lecture, we talked about what is motional electromotive force, that is due to change in area there was an induction in the current, there was induction or there was an induced EMF, that is being talked about in motional electromotive force. Today we will start with some of the problems associated with motional electromotive force. In the last lecture we talked about one problem. This lecture also we will start with one problem only. So, please understand the problem very carefully, it involved many parts. So, let me start. So, yes, for a quick reference, here all the formulas are being written and it is updated simultaneously. So, let us move on. So, the arm PQ of the rectangular conductor is moved from x is equal to 0 outwards. So, this is the PQ conductor being talked about. The arm PQ is moving towards this direction, that is out. It is also denoted by this velocity v here, that is going outwards. The uniform magnetic field, let me denote this uniform magnetic field as B. Uniform here tends that it does not change with space, it does not change with time. In that complete area, in that complete planar loop, it is constant only, which is with the value equal to B. So, the uniform magnetic field B is perpendicular to the plane, it is already known. So, now in this example, please make sure that these are dots here and not crosses, not like this. So, as I already talked in previous lectures also, any cross tells that it is going away from the screen, and dot means it is going, it is towards you, it is towards you, it is away from you. So, the uniform magnetic field is perpendicular to the plane and extends from x is equal to 0 to x is equal to b. So, this is x is equal to 0 and this is x is equal to b, and is 0 for x greater than b. So, here magnetic field is absent, in this position the magnetic field is absent. Only the arm PQ possesses substantial resistance R. This line means that the value of R or the value of resistance is R here, and it is approximately 0 for SP, it is approximately 0 for SR, it is approximately 0 for RQ. That means the total resistance is only and only due to PQ. Moving on, consider the situation when the arm PQ is pulled outwards. Arm PQ is pulled outwards from x is equal to 0 to x is equal to 2b. Please be clear that x is equal to 0 is here and x is equal to 2b is here. That means the magnetic field only is situated in the half position, it is only situated in the half position of the movement of the conductor PQ. So, next line, and is then moved back to x is equal to 0 with constant speed v. So, first of all it is moved in this direction and then it is moved in this direction. So, this is the complete problem. So, now obtain the expressions for the flux. Flux is phi b, induced EMF is epsilon value, the force necessary to pull the arm F value, and the power dissipated as joule heat, that is Pj value. So, these 4 concepts or these 4 formulas are to be used and have to be calculated in this question. Moving on, sketch the variation of these quantities with distance. So, we just need that in xy plot, in which x will be moving from 0 to 2b and y will be either phi or epsilon or f or pj. So, this is the complete question. So, let us move on to the solution. So, let us first consider the forward movement from x is equal to 0 to x is equal to 2b. So, it is moving in this direction first. So, it is moving in this direction first. The flux phi b, the flux phi b linked with the circuit SPQR. Please look that this is SPQR being talked about here. This is SPQR. So, now please focus on the ranges. The question solution is being divided into two ranges. One is for x ranging between 0 to b. So, 0 to b is the position in which the magnetic field is acting upon, and b to 2b is the position in which the magnetic field is not acting. So, phi b is nothing but b into L into x. B into L into x is only this concept here. So, b is known, A is nothing but L into x, and hence phi b is equal to b into L into x. A is area, cos theta is 0 here, because the direction of area and the direction of area and the direction of magnetic field is acting in the same direction. Now, next thing is that the induced EMF is epsilon is equal to minus d phi b by dt. We already know from this formula here. So, to first iterate you the diagram shown here. So, diagram shown here is simply that with in the location x 0 to b, in the location x 0 to b, it is simply a function of x. So, as x will increase, so therefore phi b value will increase, and therefore it is a linear graph like this. In the position b to 2b, in the position b to 2b, it will be constant, and hence the line is like this. And if we go outward, that is if we try to go from 2b to b, 2b to 0, sorry, 2b to 0, then also from m to L it will be constant. It will be just a mirror image, it will be just a mirror image here, and then it will decrease. So, this is the graph here for flux. Moving on to the next concept, induced EMF. So, induced EMF is nothing but epsilon is equal to minus d phi b by dt, derived from this, or not derived from this, copying from this. So, it is equal to minus BLV. We know epsilon is equal to BLV for a conductor. In the last lecture only we have derived that BLV, that is equal to BL into dx by dt, and dx by dt is nothing but V. So, for a moving conductor it is BLV in the position where magnitude in the position only where the magnetic field B is acting. So, in this range there will be a velocity V, and hence there will be a magnetic field B, and hence there will be a value of epsilon which is equal to minus BLV. And in the position x lying between b to 2b, as there is no magnetic field, therefore b is 0, and hence it is equal to 0. So, therefore, there will be a constant value in negative direction from 0 to 2b, and then it will be 0 value. When we are talking about invert, that is when we are moving from 2b to this direction till x is equal to b, it will be 0. But this time there will be a positive loop. Why? Because the direction of the conductor movement is being reversed. If the v was like this first and now v is like this first, the value or the direction, as velocity is a vector quantity, it is dependent on direction. Therefore, as the magnitude is differ, as velocity, if we consider velocity to be positive in the first direction, then it will be negative in this direction. Hence, therefore, there is a positive sign being induced here. So, therefore, when we are going inwards, then epsilon will be equal to plus BLV, hence we get a positive value here. Moving on. So, now when the induced EMF is non-zero, the current I is, so I is nothing but epsilon by R, epsilon is nothing but B L V by R. Please make sure it is BLV only and only when there is a magnetic field acting and the conductor involved is moving through it with a constant velocity V. This formula, this BLV formula is only and only valid at that position at that time. So, now when the induced EMF is non-zero, the current I is equal to BLV by R. So, the force required to pull the arm is equal to B square L square V by R. This is the similar formula we derived in the last lecture. So, as long as the force is acting in this position, it is equal to B square L square V by R. It is a constant value, it is not changing, it is not a function of x, and when no force is acting, it will be 0. So, it is simple again, like this and like this. When we are going outwards, if you are going inwards, then again in this position, in this area there will be no magnetic field, hence this will be 0. After this, what will happen is, because the direction of velocity is reversed, as velocity is a vector quantity, therefore, that magnitude of the not the magnitude, the polarity of the velocity will also change. If we are considering it positive in one direction, we will consider negative when going inwards. and therefore the value will be positive this time, or the the velocity, the force will be positive this time, and hence there is a positive graph being shown here for the force. Moving on to the next thing. For Joule heating loss. So, we have already derived the value of Joule heating loss, which is also equal to which is same as the magnitude of the force involved. So, now the Joule heating loss is I square R. Please make sure that P j is equal to I square R. This is squared and resistance cannot be negative. Therefore, the value of P j will always be positive. Please make sure this is the concept involved here. Therefore, as it is B square L square V by R, but this force will only and only act when there is a magnetic field acting. Outside the magnetic field, there will be no induction of Joule heat. Why? Because let me iterate the last concept involved. When we were moving the conductor, when we were moving the conductor inside the magnetic field, why was the conductor being moved? It is due to the mechanical energy. It was due to the mechanical energy, and this mechanical energy led to the electrical energy. How electrical energy was being incorporated? Because there was an induced EMF, also known as electromotive force. And after this electrical energy, where did this mechanical energy went? There was an increase in temperature, there was a heat involved, there was a thermal energy. So, because there was a thermal energy, hence the concept of Joule heating. Hence the concept of Joule heating. So, Joule heating is nothing but P j is equal to I square R. So, x lying between 0 to B, because the magnetic field is acting. So, it will be equal to B square L square V by R. The magnitude will be same as the force involved in the just previous slide. So, it will be a positive value till here. Then as the magnetic field is not acting, it will sharply drop and then go to B to 2B. This was the outward position, and we are going for the inward position. It will again go till here, and then it will surge up again. Why it will surge up again? Why it won't be negative? Because as I already told you that P j is nothing but I square R. I square R. As I square, anything squared is always positive value. Resistance can't be negative. Therefore, P j is always positive. Therefore, P j is always positive. So, this is the graph for Joule heating loss. Okay, so this was the problem which was being dealt, that this was important because I need to make you understand first of all this concept, that when the force graph was being talked about, it was negative, then it was going towards positive. But when the Joule heating loss was being talked about, then it was positive at first, then it goes to 0, but it does not go into negative direction. So, this is one of the concept I want to talk about here, and the previous concepts were only directly formula based. There is nothing to be very specific here. Only if the formulas are known, the questions are easy to calculate. But yes, please make sure that the value of theta you are deriving from this concept is very important, because if the theta value is 0, then the value of phi b will be positive here, but if the theta value is 180 here, then the phi b value will be negative. So, please make sure that the direction of B and A is very important. So, please make sure of this, and this was the complete problem related to motional electromotive force. Let me start this new concept of eddy currents. So, what is this eddy current? You have already knew about this, maybe in current electricity or in basic waves concept. So, let us move to eddy currents which are being involved in electromotive force or in electromotive induction, electromagnetic induction. So, let me iterate to you. So far we have studied the electric currents induced in well defined paths in conductors like circular loops. the magnetic fields are being induced like this, in maybe induced like this in a coil. This is a bar magnet denoted by M. So, now so far we have studied the electric currents induced in well defined paths in conductors like circular loops. Even when bulk pieces of conductors are subjected to changing magnetic flux as in delta phi b, induced currents are produced in them. This leads to induction of current. So, anything involved till now was directly ideal case scenario in which there was no dissipation of energy, there was no dissipation of heat, everything was kept ideal because the assumptions were being kept like this. So, now move to a little real life scenario. So, what happens is that their flow patterns resemble swirling eddies in water. Whose patterns? These magnetic, if any wavy nature particles or any magnetic field particles, if anything is being kept near water and the nature of those particles or the nature of this water is being told, then it was found that it is swirling nature. What does swirling nature means? A swirling nature is being depicted in a figure on your right hand side of the slide. So, this is swirling nature. This is swirling nature. So, their flow patterns resemble swirling eddies in water. This effect was first discovered by physicist Foucault. So, there was a very prominent scientist, physicist Foucault, who discovered this effect known as eddy currents. So, now we call this as eddy currents, and these currents are called as eddy currents. So, this is a new concept which needs to be dealt before we talk about the concept of inductance, we talk about the concept of AC generators. So, let us move on to understand what is happening here using an example. So, this is a copper plate. So, let us move on to the first point here. So, these 3 points are being dealt with. So, let us move on to this fourth point. A copper plate is allowed to swing like a simple pendulum between the pole pieces of a strong magnet. So, please focus on this figure for now. So, just to understand what is happening here is using a pivot on the ceiling, using a rope, a copper plate, this is a copper plate here, a copper plate was being tied and 2 strong magnets were being used. Just to denote, I wrote this as SM, strong magnet. So, strong magnet was being used and this copper plate was made to swing. So, if I depict you the scenario that this is a, let us say this is the pivot and this is the swing. So, the swing is like this, there is no pressure, there is no like this. If I do it like this, then it is like this and the bar magnets are being kept like this. So, this is the scenario talked about here. Moving on, it is found that the motion is damped and in a little while the plate comes to a halt in the magnetic field. So, because of these because of this south and north pole magnet, what will happen is, due to this there will be a magnetic field here. There will be a magnetic field here, and because of this magnetic field there is a dampness. What is dampness? That is, let us say what does dampness mean here is that if the frequency or the omega of this pendulum was large, then there is a decrease in the frequency, it keeps on decreasing, and then it is halt like this. So, this is the concept being told in the second point, that it is found that the motion is damped and in a little while the plate comes to a halt in the magnetic field. Next, so this phenomena can be explained on the basis of electromagnetic induction. Magnetic flux associated with this plate as in this, associated with this plate keeps on changing as the plate moves in and out of the region between the magnetic poles. So, the magnetic field is only and only situated in the planar area of the magnetic pole of the bar magnets. So, now as the pendulum is moving away, then there is a decrease in the magnetic flux. When it is coming inside, there is an increase in the magnetic flux. When it is going outside, there is a increase, say there is a again decrease in the magnetic flux. So, there is a constant increase and decrease of the magnetic flux happening when this complete experiment is taking place. Due to which what happening is, as we have already talked in the last lecture, that when there is an increase in flux or when there is a decrease in flux, it tries to oppose the force. So, when it is coming like this, it will try to oppose, hence the speed is increased, sorry, the speed is decreased. Then when it comes again, it tries to again decrease the speed, and that is why the speed is decreasing, speed keeps on decreasing and then it comes to halt. So, magnetic flux associated with the plate keeps on changing as the plate moves in and out of the region between magnetic poles. The flux change induces eddy currents in the plate. So, eddy currents is nothing but these small currents, very small currents, swirling nature, in let us say this is that copper plate we are talking about. So, these small currents which are being induced are known as eddy currents. Directions of eddy currents are opposite when the plate swings into the region between the poles, when it swings out of the region it is again opposite. So, what does this line tells you about is ki when, let us say I will try to depict the scenario here. So, what will happen is, let us say this is the pendulum and this is the plate here. So, and this is the region of magnetic field here. So, when it is going inside, the force is like this, that it tries to slow down when it comes, and when it is, let us say here, and it goes like this, it again tries to oppose. In another scenario, if it is like this and the magnetic field is like this, when it tries to come inside, the opposition is like this, and when it is inside and it tries to go above, the opposition is like this. So, because of this constant opposition of the frequency of the pendulum due to eddy currents, because there is a change in flux and hence there is a change in current, when there is a change in flux, there is an induction of current, this current is called as eddy current, and due to this the frequency of the pendulum keeps on decreasing. So, for this lecture let me stop here. For this concept I have told you what are eddy currents, and I already talked about the problem involved. Further discussion of eddy currents will be done in subsequent lectures. So, thank you for now.